Every autumn, somewhere around late September, the trees outside start doing that thing. The green fades, the yellows come in, and then, on certain trees, you get those deep, almost glowing reds. It's one of those things that feels like it should have a simple explanation. What nobody knew, until surprisingly recently, is that the yellow and the red are doing completely different things, and one of them is a genuine scientific mystery. So here's what you probably learned in school. Leaves are green because of chlorophyll. In autumn, the chlorophyll breaks down, and you see the true colors underneath. That's your yellows and oranges. It's a nice, tidy explanation, and for the yellow leaves, it's basically right. The yellow and orange pigments, called carotenoids, have been sitting in the leaf all summer long. They were always there, hidden behind all that green chlorophyll. When the chlorophyll breaks down in autumn, the carotenoids are simply revealed. It's like pulling a green filter off a photograph. Nothing new was created. You're just finally seeing what was underneath the whole time. Red is a completely different story. Red pigments, called anthocyanins, are not sitting around in the leaf waiting to be unmasked. The tree actively manufactures them in autumn, builds them from scratch. The leaf is weeks away from falling off the branch, and the tree is spending energy constructing brand new molecules inside it. In about 70% of tree species in temperate forests, you'll find anthocyanins showing up right as the leaves start to die. That's not a coincidence, that's a pattern. Think about that for a second. Why would a tree invest resources in a leaf it's about to throw away? That'd be like repainting your apartment the week before you move out. This is where it gets interesting, because scientists have been arguing about the answer for over 2 decades, and they've come up with 2 very different theories. The first one is the sunscreen theory. When a leaf is shutting down for winter, it's not just dying, it's running a careful recycling operation. The tree is breaking down its own chlorophyll, pulling out the nitrogen and shipping it back through the branches to store for spring. Nitrogen is expensive. Trees don't want to waste it. But here's the problem. A leaf with less chlorophyll is more vulnerable to sunlight. The remaining photosynthetic machinery can get overwhelmed by light. It can no longer process properly, and that damages the cells. If the cells get damaged, the recycling operation fails, and the tree loses all that nitrogen. So the anthocyanins, those red pigments, act like a shield. They absorb excess light energy, particularly in the blue-green spectrum, and protect the leaf's internal recycling system while it finishes the job. Under this theory, red autumn leaves aren't decorative. They're protective gear for a demolition crew. The tree is essentially saying, I need 2 more weeks to strip this leaf for parts, so let's keep the lights dimmed while I work. It's a solid explanation, backed by real data showing that red leaves handle bright autumn sunlight better than yellow ones while breaking down chlorophyll. Researchers in New Zealand even showed that the red pigments sit in the top layer of the leaf, right beneath the surface, positioned perfectly to intercept incoming light before it reaches the sensitive machinery below. Not bad for a theory about tree logistics, but there's a second theory, and this is the one that gets weird. In 2001, the evolutionary biologist W.D. Hamilton, along with Sam Brown, published a paper arguing that red autumn leaves aren't sunscreen at all. They're a warning sign, specifically a warning aimed at aphids. Hamilton, by the way, is widely considered one of the most important evolutionary theorists of the 20th century. This was one of his final papers, published after his death. So when this idea landed, people paid attention. Here's the logic. Every autumn, winged aphids migrate to trees to lay their eggs. Those eggs overwinter on the bark and branches, and when spring arrives, the larvae hatch and start feeding on the new leaves. For the tree, this is a serious problem. Aphids drain resources directly and spread viruses that can cripple the tree for years. Hamilton and Brown proposed that trees with red leaves are essentially putting up a sign that says, "I'm well defended, go somewhere else." The red color is an honest signal of the tree's chemical defenses. A tree that can afford to manufacture anthocyanins while simultaneously shutting down for winter is a tree with resources to spare. It's a tree that will fight back hard against parasites. A poorly defended tree, on the other hand, can't afford the red. It just turns yellow, and the aphids, according to this theory, learn to read those colors over millions of years of coevolution. Now, you'd think this would be easy to test. Do aphids actually avoid red leaves? The answer, from multiple studies across Europe and South America, is yes. Aphids consistently prefer to land on green and yellow leaves and avoid red ones. Researchers found this across several tree species and several aphid species. The pattern holds up. Even in controlled experiments where researchers offered aphids a choice of colored surfaces, green won every time. Red came in dead last. Most people never heard about this part. There's a piece of evidence from apple trees that makes the whole thing even stranger. Wild apple trees, the ones growing in the mountains of Central Asia where the species originally evolved, turn red in autumn. Their leaves go through the full color change. But most domesticated apple varieties, the ones growing in orchards across Europe and North America, don't. Their leaves turn yellow or just stay green until they drop. Why? Because for centuries, farmers were selecting apple trees for the biggest, sweetest fruit. Nobody was breeding for pest resistance. The trees that won the domestication lottery were the ones with the tastiest apples, not the ones best at scaring off aphids. So over hundreds of generations of artificial selection, the red autumn signal gradually disappeared. The trees didn't need it anymore. Humans were handling the pest problem for them. And here's the detail that really ties it together. The few domesticated apple varieties that do still turn red in autumn, they have noticeably smaller fruit, closer in size to their wild ancestors, and they're far more susceptible to fire blight, a disease spread by insects. In other words, the trees that kept their red warning signal are the ones that needed it most. For a while, that seemed like a clean win for the warning signal theory. Trees under natural selection keep their red. Trees protected by humans lose it. That didn't last. There's a complication that makes this whole picture beautifully messy. Aphids don't have a red photoreceptor. They literally cannot see the color red. Their eyes are sensitive to green, blue, and ultraviolet. But red? Nothing. So how can red leaves be a warning signal to an animal that's colorblind to red? The answer, it turns out, is surprisingly elegant. Aphids are strongly attracted to green. It's their primary cue for finding healthy, nutritious leaves. A red leaf, to an aphid, doesn't register as danger. It registers as not green. The red pigment effectively masks the green wavelengths that aphids are drawn to. So the signal works, but maybe not the way Hamilton originally imagined. It's less like a stop sign and more like camouflage. The tree isn't shouting a warning. It's hiding the thing that attracts the enemy in the first place. A tree outsmarting an insect by making itself invisible in plain sight. So yeah, nature's a bit much sometimes. And that's the state of the debate. Whether red leaves evolved as sunscreen or as an anti-aphid signal, or some combination of both, is still an open question. The photoprotection theory and the coevolution theory aren't mutually exclusive. It's entirely possible that anthocyanins started out protecting the leaf's recycling process. And over time, the color itself got co-opted as a signal to herbivores. Biology does that kind of double duty all the time. So next time you see a red maple leaf on the sidewalk in October, you're not just looking at a pretty thing that fell off a tree. You might be looking at an ancient chemical weapon, a carefully constructed sunscreen, a coded message to aphids, or all three at once. Scientists genuinely aren't sure yet. And that's kind of the best part. The real question isn't whether leaves turn red for one reason or the other. It's how a dying leaf became one of the most sophisticated communication tools in nature. If you're still here, subscribe. I cover stories like this every week. The kind of questions that sound simple until you actually try to answer them. Click the video on screen for another one.